In this second section, our second day of section 2.1, we're going to talk about how adding, subtracting, multiplying, and dividing a constant to each data point affects the SOC. So for transforming data, it converts the original observations from the original units of measurement to another scale. Transformations can affect the shape, the center, and the spread of a distribution. So when we're adding a constant, the measure of center and location will be added the same value or subtracted. So it adds A to the measure of center and location. But it does not change the shape of the distribution or the measures of spread. So the spread and the shape do not change, but the center will change by adding or subtracting the same constant. Look at this example. Here's the two sets of data, but one set of data we subtract 13 from every value. Look at how the shape of the distributions are exactly the same. Also, if you look at this, the spread has not changed at all. It's the same width as far as the data points go. Now, the center, obviously, as you can see, went down, and it went down by 13 points. If you look at this, our mean was at 16.02. It went down 13. Our standard deviation, which measures spread, stayed the same. Our min, our quartile 1, our median, our quartile 3, and our max all went down by 13. Notice the interquartile range and the range did not change. So again, adding and subtracting only changes the measure of center. Now, when we multiply or divide by a constant, then the measure of center and location will be multiplied by the same value, and the spread will be multiplied by the absolute value of B, but the shape of the distribution does not change. So multiplying, dividing does not change the shape. It does change the spread by the absolute value of B, and it also changes the center by multiplying by B. So here we are again. It says, because our group of Australian students is having some difficulty with the metric system, it may not be helpful to tell them that their guesses tend to be about 2 to 3 meters too high. Let's convert the error data to feet before we report back to them. There are roughly 3.28 feet in a meter. So we took the feet data and we translated it into meters, and as you can see, the shape is still roughly the same. We're skewed to the right, but our center and our spread were multiplied by 3.2. So our mean was multiplied by 3.28, our standard deviation, our interquartile range, and our range was all changed by that multiplier, the 3.28 feet.